Hi, Mitch Winger back with another video on data analytics and machine learning. In this video, we'll discuss cumulative response and lift curves. Okay, let's get started. As we saw before, ROC curves can be very informative, and they're commonly used to visualize how a classification model will perform. Of course, they're not intuitively obvious to many of our stakeholders in an organization who are not familiar with data science techniques. One of the objectives that we have in data analytics is to present information as clearly as possible, not only for buy-in from the stakeholders, but for more thorough understanding of the models by the data science team. Now, one alternative to the ROC curve is what we call the cumulative response curve, which, as it so happens, is actually related to the ROC curve. The cumulative response curve plots our hit rate, our true positives, against the percentage of population that is targeted. The idea is that near the top of our list of ranks or scores that our model has generated, we will find a greater percentage of positive cases. Let's take a look. As we saw with the ROC graph, the diagonal indicates our random baseline performance. As we target more of the population, we target more of the positive cases. What we want to see is that if we target, say, 20% of the population, we'll find more than 20% of our positive cases, and hopefully way more. We can calculate what we call lift by determining what advantage our model gives us over the baseline at a given percentage targeted. Lift tells us what kind of advantage the model gives us over our baseline, which would be random guessing. Lift should be above 1 to outperform that baseline. So as an example, if we target 20% of the population, Model C yields about 65% of our positive cases for a lift of 3.25, which we calculate as 0.65 divided by 0.2. Model D yields 45%, giving us a lift of 2.25. Now, if we decide we're going to target 50%, then Model C's lift is about 1.4, while Model D's is about 1.7. So depending on which percentage of the population we target, different models may be our best performer at various percentages. So you can think of lift as how well our model pushes up positive cases to the top of our list. Now, some people actually call the cumulative response curve a lift curve, and it's easy to see why, because you can visualize what the lift is by looking at the graph. However, it's more accurate to stick with the name cumulative response curve because we actually have another chart that's called the lift curve. Let's see what that looks like. As you can see, the lift curve itself relates back to our cumulative response curve because it can be calculated from that cumulative response curve. Each point on the lift curve is basically the value of the corresponding point on the cumulative response curve divided by the value of our baseline predictor at that same target percentage. The lift curve typically starts at each model's highest lift value, then descends gradually back down to 1, which is the quote-unquote lift of our baseline model. Be careful and specific when claiming lift values. You might hear someone say that her model provides 3 times lift without any context. Well, which threshold does this lift occur at? It's important to note that both cumulative response and lift curves are dependent on the distribution of the training data. So the curves represent performance only for that particular distribution of cases. As an example, in many situations, such as those where we're training models to detect fraudulent transactions, trying to determine response to online ads, etc., in many of those situations, we have a very low percentage of positive cases, as low as 1 in a million or even lower than that. In these situations, it's common to downsample our negative cases so that we don't have so many negative cases cluttering up our modeling efforts. And we can build our training model on more positive cases. So when this happens, the cumulative response curve and lift curve won't be accurate for what our actual population is. They are specific to whatever we downsampled our training data to look like. In the meantime, the ROC graph will still be useful. Now, that's not to say that your cumulative response and lift curves won't be useful at all. You can still actually evaluate the shapes of them for your downsampled results to have at least some idea of what you're going to expect when you apply the model to a full population. That's it for this discussion on cumulative response and lift curves. I hope you found it useful. As always, be sure to check out the other videos in the series.